Here in Chapter 4, we're going to take a look at some of the fundamental research issues. We're going to focus on variables, operational definitions, and measures of validity. The important part of this chapter is to understand the basic ideas and to be able to understand why we want to have valid studies and why we want to use operational definitions as a way to improve construct validity, as well as why we use internal and external validity as measures of good research. So let's take a look at the objectives for this chapter before we jump into it. We want to be able to define a variable and describe the operational definition of a variable. This is going to be very important for both research methods and for statistics. Describe the different relationships between variables, and really what we're looking at is the relationship between scale variables, so the positive, negative, curvilinear, no relationship. That's kind of all code for correlation. We'll talk about that in a moment. We want to compare and contrast non-experimental and experimental research methods. Specifically, we're going to talk about the exchange between internal and external validity when we're talking about non-experimental and experimental research. We want to be able to distinguish between the independent and the dependent variable, discuss the strengths and limitations of laboratory experiments and the advantage of using multiple methods of research, and then last we're going to talk about defining and distinguishing among construct validity, statistical validity, internal validity, and external validity. That's last in this item, or in this list of items, but we're going to talk about that as we go through. So let's jump into validity. And here we're going to outline the 4 different types of validity, and I encourage you to get a good understanding of this before we move on. These are all different enough to where I think that we can process them without having to decipher any of the similarities. So the first type of validity is construct validity. And maybe before we jump into it, I want to let you know what validity is. It's about the truth of our findings. Can we trust that our findings are accurate and truthful? So we do that using one of these 4 types of validity, and sometimes multiple types together. So we talk about construct validity, which is where we want to measure or manipulate something accurately in a way that it represents the theoretical variable being studied. An example of construct validity might be something like a measurement of the therapeutic benefits of having a therapy dog or an animal-assisted therapy treatment. And we want to say that, well, geez, if we reduce, let's say, anxiety by having an animal present, then the animal must be therapeutic. Well, that's a fine idea, but therapeutic value is different than calming value. You know, having a dog and petting a dog is a wonderful thing. I love to pet dogs and they make me feel good. But is it therapeutic? Maybe not, because therapeutic intervention has more to do with describing, identifying, and resolving an issue as opposed to distracting from it. Now, is it helpful? Absolutely. Is it therapeutic? Maybe not. So the construct of animal therapy or animal-assisted therapy is a fine construct, but it may not be being measured by the calming effect that the animal has. Now, to use an animal in a therapeutic way takes a lot of skilled intervention, not just simply the presence of it. So the construct validity for animal-assisted therapy needs some work in order for it to be valid, as opposed to it just being 2 ideas that tend to point to the same outcome in terms of calming, not necessarily therapeutic intervention. Internal validity is when we want to be sure that the accuracy of our conclusions are based on cause and effect. So when you think of internal validity, think of like an experimental design to where we control things so precisely that the only possible explanation for the outcome is based on the treatment that we gave to that individual. For example, we could talk about medication trials. It's a pretty concrete example, and it makes some sense with internal validity. So if we had 10 people and we had them stay in a laboratory setting, maybe a housing situation, and we wanted to have them on a medication for 5 days to see if the medication reduced some kind of hallucination. And the only thing that was different about every day and every situation for the individuals was the medication that they were given, then you can be reasonably certain that the medication was the difference in whether or not people had hallucinations, rather than some kind of other explanation like maybe an extracurricular activity or something like that. So when you have a tightly controlled experimental design and you think that you have a result that is due to the treatment effect, then you can say that it has high internal validity. Now, when you have internal validity, what you're saying is that everything inside of the test or the experimental design was controlled for and there aren't other explanations for it. What you are lacking or what you are exchanging that for is what's called external validity. And external validity is whether or not the results of your study can be generalized to other populations and settings. In the example that I gave with the medication, if you are in a situation that is not like other situations that you experience in life, so if you're spending 5 days in a setting to where you are going through the same regimen every day and it's tightly controlled and everything, that does not generalize well to the public, meaning that you can't generalize those findings and say that the findings that you had in the study are like what you would expect in everyday life, because everyday life is so much more complex and involves a lot of different variables. So what you're exchanging with internal validity is the fact that it's difficult to generalize the findings to other populations. Not that one is wrong and the other is right, but when you're thinking of doing a study, you have to think about what you're trying to do. Are you trying to suggest that the treatment has an effect, or are you suggesting that the treatment can be externalized or generalized to other populations? So internal validity is drawing conclusions about cause and effect inside of a study. External validity is about indicating that your study has some merit outside of itself, so it can be generalized to other populations and settings. And then last is statistical validity, the accuracy of the statistical conclusions drawn from the results of a research investigation, meaning that if you are doing a research design and you want to know if there is a correlation between two variables, for example, how tall you are and how likely you are to go on a date on a scale of 1 to 10, you would do a correlation design. But if you ask that question, is there a correlation between height and the likelihood of going on a date, and you did that using a design where you looked at tall versus short people and how likely they were to go on a date, you would be making a mistake. And it's a very subtle mistake, but it's still present. When you compare how tall you are to how likely you are to go on a date, and you're using a correlation method, you need to measure yourself in inches in order to determine how tall you are. And that's the correlation design, where we use two numerical variables. So how tall you are in inches and how likely you are to go on a date on a scale of 1 to 10. However, if you just say, well, tall people are more likely to go on a date than short people, what you've done is you've accidentally done a between groups design. You've compared the means of two groups as opposed to looking at two variables. It's a small but meaningful difference, and we'll talk more about that when we talk about t-tests and statistics and correlation tests and statistics. But just know that statistical validity is the accuracy of the statistical conclusions based on whether or not you did the right particular test, or if the numbers that you got were derived using good sampling strategies and measuring all kinds of assumptions of the test and everything. I'm not so concerned right now that you are able to describe statistical validity. I'm more concerned that you're understanding construct validity, internal validity, and external validity, because we'll talk about statistics in statistics class. When we're talking about doing research, we're talking about variables, and variables are these containers. We've talked about this in stats class, but variables are these containers that have different values. So a variable needs to be some kind of construct, some kind of idea that can have more than one value to it. So we have variables that are in everyday life. A variable, what are you going to eat for lunch, is a variable. It has multiple values. How much gas can you put in your car is a variable. That's the number of gallons or liters, however you measure gas for your car. Any kind of variable must have containers, so it must have levels, so it must have two or more levels or values. So if we had a variable called are you alive? Yeah, well, okay, the variable are you alive technically has more than one level. It has two levels, yes or no. But you cannot answer the question, are you alive if you're dead? So technically it's really not a variable because you are alive if you can answer the question. If you cannot answer the question, is you're dead and you can't answer the question. So it's a non-question. You also talk about values. So we need to have different values. If you ask the question, how old are you? That's certainly a variable. The variable is age or how old are you, and it has many different values to it. We encounter variables in everyday life, and a variable is not something that's overly complex. Some people get confused about variables. So I don't understand what a variable is. Usually because you're overthinking it. A variable is very simply a construct that can be measured or it can be grouped if it's in terms of a group. What's your gender, for example? That's a grouping variable. So there are lots of different examples for variables, and variables help us to define our operational definitions. So the operational definition is a very important concept in research methodology. The operational definition is how you are trying to identify your variables. It's how you're choosing to measure something. So an operational definition can seem very simple if we rate it in terms of something like age. How old are you? The operational definition of age in most cases is years. So I'm going to define age as the number of years that you've been alive. Now, it seems very self-evident, but we can't brush it under the rug because it seems easy. When I ask you something like, how sad are you? Think of all the different ways that you could answer that question. You could show me with your face how sad you are. You could tell me on a scale of 1 to 10 how sad you are. You could use a Beck depression inventory, which would be more about depression, but it's still a tightly connected construct. The operational definition is how you are specifically choosing to measure a variable. Think of a variable like sex. What is your sex? We could use a couple different operational definitions of sex. We could use an operational definition that says that you are going to report your external sexual genitalia in terms of what sex you are. We could also define sex as the types of chromosomes that you have. We could also define sex as the amount of a hormone that is present in your body or the biochemistry that you have. There are lots of different ways to identify somebody's sex, especially when there's some androgynous features. For example, somebody who was born intersex or having multiple different types of external sexual genitalia. There are lots of different operational definitions for many constructs. When we think of your operational definition, think of the way that somebody is choosing to measure the variables that they're interested in. Okay, it can be a scale. It can be, for example, the Beck depression inventory, where you answer a bunch of questions and it cranks out a number, and that's how depressed you are. We could also look at something like racist attitudes using the implicit bias test. So we can measure something about racism in terms of what you know about yourself and how you think about other types of people. Now, when we have an operational definition, it needs to match the construct that we are measuring. So I mentioned earlier that if I asked you about sadness, which is a feeling, it's a transient feeling that comes and goes, and it's usually based on situations and things like that, which is probably another operational definition. But if I said I'm going to measure your sadness based on the Beck depression inventory, I mentioned that those are two tightly connected ideas, depression and sadness, but they may not be exactly the same. So that might suffer from what's called poor construct validity. If I measured sadness using the Beck depression inventory, I would probably have moderate to decent construct validity because it would be pretty much measuring the construct of sadness well enough. It's not perfect, but it's okay. So you might choose something else besides the Beck depression inventory to measure sadness. The idea of construct validity then is, does it reflect and measure what I am trying to measure? Is the way that I'm trying to measure something accurate? Is it precise? So if I wanted to measure somebody in terms of how many cell phones tall they are, that's an okay way to measure somebody. It's not very standard. So it's technically sound for construct validity, as long as I measured everybody else in the number of cell phones tall that they were. But generally, it's not a good way to do it because it doesn't match other ways that are commonly used to measure somebody. So construct validity, again, is, does something reflect the reality and measure what it claims? Is the construct being measured appropriately? This is a fun way for us to measure something. So this is the Wong-Baker Faces Visual Analog Scale. This is something you've probably seen if you've been to a hospital. This is developed by Wong and Baker way back in 1983, the year I was born. Wow, that's a long time ago. And it's a way for people to describe how they feel visually, numerically, and verbally. So they could look at any of those and see which one they most relate to, and they can talk about it in terms of the number that they are, the face that they are. You can just point to it, or you could say, well, it looks like it hurts a little more, so I guess that's the face that would describe me. Those are all three different ways to measure the same construct of pain. And again, there's a lot that goes into this, a lot of research about pain science and the faces and everything. And even the color that the faces are makes a difference. So it's very interesting, all the research that goes into it. You can go into it. But if you want to research the Wong-Baker faces and come to an understanding of why they chose those and the color and everything, you can Google them using a Google Scholar and determine how they came to those. Okay, so now we've seen some operational definitions. We've talked a little bit about variables. Let's talk about the relationship between variables. We're going to look at a very specific set of relationships between variables, and we're going to be focusing on just the way that variables correlate, so the way that they move together. Now, we'll be talking about correlation in stats class toward the end of the term. And it's pretty simple to understand, so I don't think that this will throw you for a loop not having an understanding of the statistics of it. As a matter of fact, it might be easier without that. But let's talk about some relationships between variables. Now, there are linear relationships between variables, and we're talking about scale variables, so those variables that are measured numerically. So a positive relationship between two variables is that as one variable increases, the second variable also increases. So think of something like grade in school and shoe size. So as you get into a higher grade, your shoe size also increases because we normally developmentally grow from, kindergarten on up through the end of high school. There might be a little bit of a plateau effect that happens in high school, but generally we keep growing through that period. A negative linear relationship or a negative correlation is that as one variable increases, the second variable decreases. So as your amount of homework increases, your free time decreases. So that line would be negative. We'll take a look at some examples of that in a moment because there's a summary slide here after we're done talking about the curvilinear relationships and the no relationships. So the curvilinear relationships, they form curves. So a curvilinear relationship is either an upside down U or a U-shaped distribution that measures something that starts low and peaks and goes low again, or starts high, goes into a dip and then goes back up again. So let's take a look at the age and amount of free time. So just age, I wasn't particular. Maybe this is by decade or whatever. But let's say that we have how old you are from 0 to 8. I just threw numbers in there. It's okay. So let's say that this is 20 years old, 40 years old, 60 years old, 80 years old. And the amount of free time that you have on a scale of 1 to 5. So generally, the younger you are, so if I'm, between 0 and 20 years old, I have, a fair amount of free time. As I become 20 years old, I start to lose that free time. You have school and things like that. Then you get into a job in your 20s and 30s and 40s. But after your 40s, maybe you start to get more free time because other things in life have dipped off and you don't have, maybe the kids have moved out. And then you retire around 60 and then, you start to have a lot more free time. So a U-shaped curve is demonstrated by some kind of higher frequency at the beginning and end of the x-axis and a lower frequency in the middle of the x-axis. Now, the enjoyment of your favorite food. So if we talk about enjoyment, like on a scale of 1 to 5, how much do you like your favorite food? And like, well, geez, I really like my favorite food. Okay, what if you didn't have much of your favorite food? You wouldn't have much to like. But then there's that sweet spot to where, I have just the right amount of my favorite food, so I really, really like it. I'm in that sweet spot. And then after you have so much of your favorite food, maybe you kind of get bored with it again. So you kind of have this inverted U shape to where there is a lower occurrence of something on the left side or the smaller side of the x-axis, and then it peaks in the middle of the x-axis and then it dips back off again. These curvilinear relationships are kind of advanced in how we interpret what they mean, but generally you can make an assumption about this, and if you remember anything from econ class in high school, this is kind of one of those diminishing return curves. So, there tends to be a peak and then a diminishing return afterwards. If you don't remember that from econ, that's okay. I'm not going to hold it against you. It's fine. Next is relationships between variables where there is no relationship. So let's take a look at this graph real quick. This is on a scale of 0 to 14. And this is the grade that you're in. So 0 might be kindergarten, let's say. And then you have first grade, second grade, third grade, fourth grade, all the way in up to 12th, 13th grade, whatever. It's fine. It's okay that it went off. And then you have the number of people in each classroom. And you can see that even though there seems to be a lot of spread here, look at the scale. It's from 23 to 26. So in an average classroom from kindergarten on up to 12th grade, let's say, there are somewhere between 23 and 26 people in the class. There is no real systemic change that goes on here. There's not an increase over time generally of the number of people in your class. So the relationship between this variable is that there is no relationship. You can't see a downward or an upward trend. Now, in college, you might see something a little bit different. You might see that you have more people in the freshman level classes. So in your first year, you have more people in your class. And then through your senior year, you start to get fewer people. That is certainly the case, but generally from K to 12, you don't have any variation in the amount of people in your classes. And if you do, it's very small, still between 23 and 26 people in general. This is a summary slide that looks at different examples of positive correlation, negative correlation, an inverted curvilinear relationship, and a no relationship. And for this slide, I encourage you to take a look at the description in the book. This is taken right from the book. So if you want a description of what these variables mean, then you can take a look at that. I'm not going to spend a lot of time on that right now. Now, all of these variables are governed by the idea of correlation. And the correlation coefficient is a number that describes how correlated two variables are. So if we have a correlation coefficient, which is just a number, so a correlation number, the correlation coefficient has a possible value from -1 up to 0 and up through 0 and to +1. So a perfect negative correlation is -1. If you have no correlation, it's 0, and there's a typo. If you have a positive correlation, it's +1. We're going to cover this more in stats class. I'm not going to worry that you know about all of this right now. Switching gears, let's talk about non-experimental versus experimental methods. And when I say experimental methods, we're talking about situations to where we have maybe two groups of people and you randomly assigned everybody to one of the two groups. You tested one group and the other group was a control group and you looked to see what the differences were. That's a very basic example of an experimental method. A non-experimental method is when we are taking people and they already have differences. So let's say that we wanted to take a look at the difference in Hispanic and Asian students and their performance on the SATs. That would be a non-experimental method because we're looking at existing differences. We aren't separating them into different groups based on random variables. We are purposefully using their existing characteristics in order to group. Now, when we talk about experimental methods, we're focusing on internal validity. Can we make conclusions about causal relationships? Can we say that there was a change that was caused by the treatment. Strong internal validity requires three things. The first is temporal precedence, meaning that A causes B, and it happens in that order. We'll look at some examples. We also look at the covariation between the two variables. If A occurs, B occurs. If A does not occur, then B does not occur. We want to see that the two variables vary together, so they co-vary, so covariation. Then the last is that we want to make sure that there aren't any alternative explanations for what we found. There's a pretty common example of alternative explanations that you've probably heard before, is that crime and ice cream sales increase in the summertime. So is there a relationship between them? Probably not. I don't think that people who are getting ice cream are driven to commit crimes, and people who commit crimes probably aren't rushing out to get ice cream. Probably the alternative explanation is that there is summertime, and in the summertime people are more likely to be out and committing crimes because, well, it's not freezing cold and 3 feet of snow on the ground in Michigan, and they're getting ice cream because it's blistering hot in the summer, and ice cream is a fun summertime treat. So we want to get rid of the possible alternative explanations when we do internal validity. So external validity, the extent to which the result study can be generalized to other situations. When we have an experimental design, and I mentioned this earlier, when we have an experimental design and it's done in a laboratory type setting or another highly controlled setting, we are suffering, that's not really a good word for it. We're aiming for internal validity. But when we are using these field experiments where we are finding how people naturally behave in the world, we are looking at external validity. We want there to be good external validity in these cases, which means that we want the we want the research that we're doing to reflect reality as much as possible. When we do a field experiment, we're trying to do something in a natural setting without impacting the participants as much as possible. Now, there is less control. We can't say that one thing caused another generally because we don't have control over all the other possible explanations. We also run into ethical and practical considerations because we have these things called participant variables. We can't assign people to a race. We can't line up 10 people and say, you're going to be Asian, you're going to be Hispanic, and you're going to be a Pacific Islander. We can't do that. People have their own races and ethnicities already. So these participant variables cannot be manipulated, meaning that we're probably not going to have an experimental method if we must have a variable like age. If we want to know if there's a difference between freshmen and seniors and how much homework they do every week, we will need to do a non-experimental design because we can't randomly assign individuals to different groups because people already belong to the groups. So the participant variables cannot be manipulated. People already have them. Now, the non-experimental method, again, is when we want to look at how people behave in natural settings to see if things vary together. So we want to see, generally, if two variables change together or not. There are two major challenges to the internal validity with the non-experimental method. We can't always tell cause and effect. So if we're looking for this wonderful cause and effect thing and we want to know if the race you are causes you to have a higher SAT score, we're going to be in bad shape because we can't tell cause and effect based on that because we can't systematically change somebody's race or ethnicity. We have to leave it alone, so we can't get to that good cause and effect. The other thing is that even if there were you got it dead to rights, you have one race performs better than another race on the SAT, you can't rule out the fact that something else might be causing that. There might be cultural biases in the test itself. So you can't always know that there isn't a third variable problem, that something else is causing the outcome. Sometimes we call these extraneous variables. So if we wanted to know if there was a difference between Asian students and Pacific Islander students to see if there is a difference in how they perform on the SAT. An extraneous variable could be something like culture. There might be a different culture surrounding school for Asians compared to those people who are Pacific Islanders. And if there is that difference, then you can't say that the reason is because simply they are labeled as Asian or Pacific Islander. It has to do with culture. And we know that culture is something that is much more various in a group of people than race is. For example, if I identify racially as white, I know that there are many different types of cultural influences among people who also identify as white. And what that means is that I can't just say that I scored better on a test because I am white. I would have to say that I scored better on a test because I'm white with all these different considerations. That I'm a Midwestern person, that I am in academia, blah, blah, blah. All the different other variables get tied into it. If the variable that surrounds me causes an issue, for example, if I am white and I score better on a test, and it's because of something like I am in academia and I have an advanced degree, all of a sudden that advanced degree becomes a confounding variable, meaning that my advanced degree and the ability to take tests and things like that is what's causing the increase in my test scores, not that I'm white. Okay. So when you think of an extraneous variable, think of the other possible things that could be explaining what the change is, and if those are causing the change, then they're considered confounding variables. Not the variable that you're studying, but this other variable that's also tied in with it. This is a short breakdown, a graphical representation of the problems that happen within non-experimental designs and how experimental methods are a little bit better at declaring internal validity using the directionality problem and the third variable problem. Again, the directionality problem is, in this example, it's exercise and anxiety. Does exercise lower anxiety? Or is there some kind of increase in anxiety that decreases exercise? So we don't know which can cause which. Okay, so that's called the directionality problem. The third variable problem is that something else can be related to exercise and anxiety. So higher income leads to both lower anxiety and more exercise. Okay, so maybe somebody who has a little bit more income has the ability to pay for things without having to work as much, so they have more time to exercise, and they might have less anxiety about making ends meet. So when we talk about the directionality problem, the third variable problem, these are things that we need to balance when we're thinking of how to do research. Are we going to try to rule something out? Are we trying to control everything so that we can make a cause and effect assessment? Or are we going to sacrifice that in order to get a good outcome that matches what we would expect to see in the world? Now, when we're talking about non-experimental and experimental methods, we also need to consider two very important concepts called the independent and dependent variable. We're going to be talking a lot about this in statistics class, so between what I'm mentioning here and what is in the book, I think that we're going to be okay with it for this chapter, just leaving it at that. But the independent variable is a variable in the study that's believed to be the cause of the effect on the dependent variable. Let me put that in different terms. We've been talking about this example in the last couple of slides about race and performance on the SAT. And by the way, I'm making all this kind of up, so don't take this for my research, okay? But the independent variable is race. And let's say that, again, we're talking about Asians and Pacific Islanders. And we want to know if there is a significant difference between Asian SAT scores and Pacific Islander SAT scores. Our supposition is that there is some kind of difference between Pacific Islanders and Asians in the dependent variable SAT scores. So we think that the race will lead to an effect in the SAT. So race causes SAT scores. That's what we're supposing. We have to be careful, though, because we can't just run around saying cause and effect statistically, because it's really difficult to find causation. Especially because there are really only two different experimental designs where you can find cause and effect, and it's really that double-blind gold standard experimental design that we'll talk about later on. The other is a time series design based on case studies. So there's really only two that we can look at cause and effect. So we have to be careful when we say cause and effect. But it is okay to say that the independent variable leads to a change in the dependent variable. Now, we also manipulate the independent variable. It makes it sound bad. It's really not. But when we talk about manipulating the independent variable is, how are we grouping people? How are we grouping the levels of independent variable? For example, I could list race as, maybe the 5 races that you typically see. You have Asian, Hispanic, white, Black, and Pacific Islander. Those are kind of the 5 big ones that you see. And I could say that I'm going to look at the difference between those 5 levels of race and how they do on SAT scores. I could also say I'm going to look at whites compared to everybody else. Okay, that could be another way of manipulating the independent variable. And we could come up with many different ways. We could also do it subculturally. We could say that Midwesterners, so people who live kind of in the Michigan area of the world, will have different SAT scores than people who live in the South. So we could manipulate that independent variable in order to explore differences between groups as we see fit to separate them. So the independent variable is said to lead to a change in the dependent variable. Some other interesting tidbits about the difference between experimental and non-experimental methods is that when we are looking at experimental methods, again, those highly controlled experiments, in order to find cause and effect, we have to exercise what's called experimental control, which means that these extraneous variables are controlled by making sure that every feature of the environment except the manipulated variable is held constant. Boy, that's a mouthful. What does it even mean? So let's say that we want to know if people study better in different settings. So let's say that we wanted to conduct an experiment where we have a kind of a library setting. We have 5 people in a library setting. And we have them sitting at their study tables, and they're studying for just kind of a general knowledge test that we're going to give them. Then we have 5 people that are trying to study at a football game. And certainly that's a very different environment. But let's say that they're at the game, and we're trying to see if people can study well when there's a lot of distractions going on. Well, let's say that if we have 5 people in the library and 5 at the football field, let's say that 5 people at the library see some friends that come in the door. Okay, that's nice, fine. But the problem is that they might be influenced by their friends coming in, and we can't control for that. Now, it'd be a poor experiment because we could probably set it up so that nobody could come in. But let's say that it happened. We have people that come in through the door, and at the end of all of this, we find that there is no difference between library settings and football settings in terms of studying. And our conclusion is that, boy, it really doesn't matter. If you are at a football game studying, or if you're at a library studying, you're going to get the same results on a general knowledge test. We'd be wrong, because we would have accidentally fell victim to a confounding variable, that you had friends coming in to distract somebody. Now, what we can do is we can use something called randomization. And we could randomize something so that we have people that are in one group in the library, another in the football field, and let's say that they're equally likely now to run across friends. So let's say that one person in each group now has a friend that comes in and distracts them. That's actually okay, because we've randomized something. We've made it so that each group is equally as likely to have a friend come in and distract them. We can do that. If we use a little bit more, something along the lines of the participant variables, let's say that one person in each group has a problem with studying, so they might have something like attention deficit disorder. Let's say that we know that ahead of time. We ask people, we say, okay, you want to be a part of this study. Do you currently have any problems getting distracted while studying? And let's say that 2 people said, yeah, I do have a problem with studying. You say, okay, that's okay. You can still be in the study. But what we would do is we would put one person in each group so that each group has somebody who struggles to study, and that would make the groups equal. So we can control for the way that we separate people into groups, either through purposefully sorting out particular variables that are interesting, or by randomizing and making it equally likely that people are going to have the same kind of extraneous conditions, that they're going to experience the same restrictions that aren't related to our experiment. In cases where we cannot or should not manipulate the participant variables, then we have to work with them and do more intentional sorting, like I alluded to in the slide prior to this one. So sometimes we can't sort those out, and it's a good reminder to understand that when we have participant variables, we cannot change them. We should leave them alone and figure out a way to sort people based on that. Now, when we have an experimental method, again, that's that highly controlled aspect where we are trying to find cause and effect, we need to think about the experimental method that we're going to rely on. And in the case where we do want to have all that control, then we need to think about the research that we're going to do. We want to find a prediction. We want to use existing research in order to guide our own. So we want to work, when we can, we want to work with randomized groups. We want to sort them randomly, and hopefully we would have nobody who would be systematically changing the outcome. We need to make our predictions, and sometimes we can do that without cause and effect. As a matter of fact, prediction is technically based on correlation, which is certainly not cause and effect. It's just a relationship. Lots of times we'll use multiple methods to study a phenomenon, both experimental and non-experimental, in order to get a better understanding. So for example, if we had an experimental design to where we had 10 people in 2 groups that were doing a taste test, and we wanted to see if smelling had an impact on how much they liked a particular food. And we had 10 people in one group that had their noses plugged somehow, and then we had 10 people that were able to smell the food. We could ask them to taste the food and rate how much they enjoyed the taste of the food. And we might find differences. But what we might also do is use a qualitative method and say, okay, I want to interview you and ask you a few questions. When you looked at the food, had you had that food before? Okay, and if they say yes, then you ask them if they actually enjoyed that food. And they said, well, yeah, of course I do. Well, what we would be doing is we would be supporting an idea about how people answered the questions with prior knowledge based on those qualified answers that they gave us. So we could use multiple methods, a non-experimental method and an experimental method at the same time in order to get our results. So don't worry if you're feeling restricted. You can use multiple methods generally to conduct research. A little bit of a caveat to that is that in many cases in undergraduate and even some graduate research, you're discouraged from doing multiple methods because it takes a lot longer and it doubles the amount of work that you have to do. Nobody wants to do that. So to summarize, I know we talked about an awful lot, and I hope that you're able to take this and kind of tie it into the reading so that you can get a little bit more context for some of the things that are a little bit fuzzy to you. But we covered 3 different basic types of validity. The construct validity is the adequacy of the operational definitions. So how much did what we're measuring actually measure what we intended to? Internal validity is the ability to draw conclusions about the causal relationships by looking at temporal precedence, the covariation, and ruling out possible other explanations. And then external validity is how well we're able to generalize to other populations and settings. And remember, generally, experimental designs have higher internal validity, and non-experimental designs where you're working with participant variables tend to have higher external validity. So that was Chapter 4, the fundamental research issues. I encourage you again to take a look through the book if you're a little bit fuzzy on some of these things. If you have any questions, feel free to reach out, and I look forward to seeing what you can do with your article responses.